Hello, it's Keith here, and this is lesson 94 of the platform-specific series of my Z8 assembly programming tutorials, and we're looking at the MaxTile driver for the Enterprise, the Airline Enterprise. MaxTile is my software tilemap code. It's multi-platform, and so we can run this example on lots of different systems, even ones that aren't Z80 based. So what we're going to look at today is the single draw tile driver for the Enterprise system. It does various things that are worth noticing. You can see we are flipping our simulated sprite. The simulated sprite is just a miniature tilemap, but we also have some special tile types. We have double height. You can see those background tiles are stretched twice the height. Twice the height means half the bitmap data. It's designed as a memory saving thing because we can have a tile that uses half the memory and still looks pretty good, but it's also it's a little bit faster. We also have fast fill tiles, these background tiles here that are filled with just 2 bytes there. And we have all of the flipping, and we also have transparency. You can see if we wait for a moment, the chibi code that comes across diagonally, this one uses 0 byte transparency. So if a byte in the source pattern data is 0 byte, then it's not drawn to the screen. So simple transparency. So that's what we're going to be looking at today. Okay, well, let's go over to our source code and let's take a peek. Okay, so here is the files we're going to be looking at. This was the example you just saw, and this is the source code for the tile driver. Now I should say that MaxTile is pretty complicated, but if you don't want to use the whole of MaxTile, just take a look at the tile drawing routine. It draws an 8x8 tile, and you can reuse it in anything you want, and just ignore the rest of the code. Worth doing because, as I say, it does X and Y flip, which is quite nice. Now MaxTile uses 3 caches, so we're defining those 3 256-byte caches in the unused area of the screen memory bank. So the C000 to quadruple F bank is the video memory, but some of that is spare, so we're using some of it for our caches, and also the 256-byte X-flip lookup table. We don't need a Y-flip lookup table. The screen memory is going to start at C000, and we're defining a 256 by 192 screen. This is good for multi-platform, and it also makes the memory calculations easy, which means we can draw those tiles a little bit faster because these Z80 systems with their software tile maps are a little bit slow, so anything we can do. So we're defining our screen height as 192 lines tall, and we are defining our memory layout here. So we're basically defining all of the lines here with this table here. And we're defining our color palette here. So this is defining our screen, and basically that is going to set our screen up. Now what we're going to look at now is the actual draw tile routines. However, before that, we just do need to discuss the pattern data. So there's 2 kinds of pattern data we define. Firstly, there is the fills, which are just 2 bytes per pattern. The rest are all 16 bytes per tile pattern. So they're 4 color patterns, and so 16 bytes. And so we've got various offsets here. So I think that's pattern tile number 128 here, and 256, and so on. And these are used by the draw tile routine. Okay, let's take a look at the routines themselves. Now, when we are drawing the entire tile map, we use the screen base here. But when we are wanting to draw just a simulated sprite, which is actually a miniature tile map as well, we use this getScreenPos function here. Now, basically the calculation is very straightforward. Because of the 256 pixel wide screen, it's actually 64 bytes wide, and it makes the memory calculations very easy, actually far easier than the CPC. So the screen base plus the Y line in pixels times 64 plus the X pos in bytes. That's all we need to do. Now when this routine is executed, the C is the Y coordinate and the B is the X coordinate. However, these are in logical units, which is pairs of pixels. And so to convert that into bytes, we are basically shifting to the right the X position by 1. The Y position, we are rounding to a half tile here. Basically, the reason for that is this makes the memory calculations more convenient within the tiles. So we're making some assumptions there, and we're assuming we're only going to move in half tiles. That means we can more efficiently update the memory addresses in our calculations. So we're taking that, we're storing it here, we're effectively multiplying that by 64 here, the Y line here, adding the X and adding the screen base here. C000 is the screen base, and returning. So that is calculating our VRAM destination for drawing our tile map. Now most of the code is multi-platform, and that's the whole point of this, and I have got a tutorial series on the multi-platform MaxTile code. So what we're going to look at today is just the draw tile routines. Now when this is executed, basically we will be passed the tile map in BC, and there's 2 bytes per tile number. And we will have DE containing the source pattern data, and we're going to calculate the source pattern. HL will also point to the VRAM destination, but that is HL in the shadow register, so you can see we're doing an EXX here. And we're going to use stack misuse to actually read our pattern data. Now, at the start of our code, we did have a routine called do EI. That's a macro. And on this system, we're enabling interrupts. On some, we never do those. So rather than using enable interrupts, I often use do EI. And that allows me the flexibility to enable interrupts on the systems which it's possible and not do so on the systems that it's not conveniently. So that's what I do. Now, what we're doing at the start of this routine is we've actually already shifted one bit out of the first byte of our tile number. The least significant bit is the update bit. Now, if the update bit is 1, we need to redraw the tile. If the update bit is 0, this routine will never have been executed. So that must have been 1 for us to get here. But that bit has been pushed out because we want to replace it with 0. So the first thing we're doing here is we're testing the next bit along. Now this is the P bit, this is the program bit. Now the program bit basically defines if this is a simple tile or a complex tile. It's kind of a binary tree. We want to get to the simplest options as fast as possible because we're going to run this a lot of times. The simplest option is an unflipped tile. So if that bit is 0, we're just going to fall into this next part of the code. We're shifting the accumulated to the left by 1 bit, effectively pushing a 0 bit in because we have updated this tile and we don't want to draw it next time. So we're writing that tile number back into the source tile map. We've cleared the update flag, basically all that's done. Now what we're then doing is we're clearing the bottom 4 bits. Now each of our tile patterns is 16 bytes, and so by using those bottom 4 bits for the update flag, the program flag and the X and Y flip flags, we're basically almost multiplying our tile number by 16 here. So that's the bottom part of our tile number here. We're adding E, which is the offset to our pattern data. We're then loading the high byte of the tile number and adding, and with the carry, the D part. And so H and L now contain our source pattern data. But we're moving that into the stack because we're using stack misuse. When this is executed, interrupts will be disabled, so we're safe to do this. And what we're going to do now is we're going to transfer all of our source pattern data from the stack pointer to our VRAM destination. Now, we're going to use the C register as a quick way of adding one line, 64 bytes per line. So to move down, we add 64 to H and L. But we're going to load the L part of H and L into the accumulator because we don't need it for anything else. So we pop 2 bytes out of our source pattern data and we write E and D onto the screen. We then add C, which is 64, to L, effectively moving us down 1 line. And we then do the same again for the next line. We do this a total of 4 times, but on the 4th time, we actually, after we've done this, once we add C to L, this will effectively reset it. What we now need to do is we need to increment the H part. So we're doing that just here. Now that has effectively updated the HL pair, and that is why we were assuming that we were going to be aligned to a half tile here, because if we weren't, then these calculations would have become more complicated. So that's what we've done there. We've now done half our tile, and so we do the same for the remaining tile. So just repeatedly popping DE and writing those to the screen. Now once we've done an entire line, we're about to do one last add of C to the L part. That effectively resets it. We decrement H, moving us back to the start of the tile. We're now back at the far top left of our tile, and then we simply return. Now there is some platform specific code on the MaxTile routines. So for example, after a tile has been drawn, we're moving across one tile here by incrementing L twice. We don't need to increment H to go across the screen, and to go down the screen we increment H twice, moving us down 1 full tile, the enterprise screen. The byte data is the same as the CPC, but the layout of the lines is very, very nice. I far prefer the enterprise one, to be honest. So there we go. So that is the most simple tile drawing routine. Now in the case of the advanced version here, so what we are doing here now is there's more going on than just the most basic tile, so we need to decide what. Now if the X and Y flip bits are 0, then this is known as a custom tile, which is a super special kind. Otherwise then this is some kind of flip, and so it's just simply a case of deciding what flip. So we are here clearing the update bit here, and then what we're going to do is we've now decided we're doing some kind of flip, so we are getting our pattern offset into the stack pointer here, and then we are once again loading the first byte again, and we're going to compare the flags and see what kind of flip we're doing. Now if the Y flip flag is set, we're going to jump over to Y flip here, but if only the X flip flag is set, we're going to end up here. Now we're going to use the lookup table to do the flipping. So we're loading the B part of the BC register to the top byte of the lookup table. Now the lookup table we defined in spare memory here, and what we did at the start of our code is we pre-filled that lookup table with all of the equivalent X-flipped bytes from a source byte, and so the top byte of the HL pair is the address of the lookup table, and the bottom byte of the HL pair is the byte we want to flip, and then we write to that memory address the equivalent flip byte, the equivalent of that L byte. So we're loading the accumulator with L here, and we're taking the 2 bits that define the color for each of the pixels, each of the 4 pixels in that byte, and we're shifting the bits of those pixels to the equivalent opposite position, and we're then writing that into the destination here. So that is calculating the flipped equivalent of L effectively. And so all we need to do when we want to employ that flip table is basically we're popping DE, our source pattern data again, but this time first of all we want to write the D part to the screen. So what we're going to do here is we're basically taking D and we're loading that into the C register. The B register is the lookup table, and then we read from BC, and the byte we read back is the equivalent flipped version of C, which is we've loaded with D that we wanted to flip. So we then just write that byte to the screen. We then move across the screen and do the same for E, loading C with E, loading in from the lookup table in BC and writing that flipped byte to the screen. We now need to move down a line. We've used C this time, so we can't use C for our addition here. So this time we're adding 64 minus 1 here effectively to L here. That moves us down a line, and then we do the same again. We do our 4 lines, and then we increment H again, and we do our remaining 4 lines, and then we fix up HL, and we're done. So a little bit more complicated, but it's not too bad because of that lookup table. If we were bit shifting all of the bits around, this would be far slower, and the code would be much longer as well, so it might not actually end up saving as much memory as we might think. The lookup table is definitely the best solution for X flipping. Okay, so that's our X flip. What about our Y flip? Well, our Y flip code is all the way down here somewhere. The code's a little bit odd because I'm using some jump relatives, so it's sort of optimized for that. So here we've got the Y flip code, but we're checking the X flip flag, because if that is set, then we're doing an XY flip. What we're basically going to do is we're going to move to the last line of our destination, reading the source as normal and draw it to the screen backwards. And so to do that, we've got C again. C is 3 this time, so we load that with 64. So we basically subtract 64 from the L part and increment the H part, and that effectively moves us 7 lines down. So all we do now is we pop DE, we write that pattern data from the source pattern to the screen, but this time instead of adding C to the L part in the accumulator again, this time we subtract it. We do that 4 times, and then once we've done it the 4th time, we decrement H, and so this is effectively just writing the data backwards up the screen. Okay, so that's pretty straightforward. And then the XY flip version is basically a combination of both tricks. So we are working backwards through the destination going up the screen, but this time we're using the lookup table as well. So once again, we're loading our pattern data from the stack pointer using stack misuse to read the pattern data, and then we are loading that into the C part of the BC pair. The B part is pointing to the lookup table. And we're reading the flip data and writing it to the screen, going across the screen, and then going up, writing the data to the screen here. So there we go. So as I say, both techniques being employed there to do the X and Y flip simultaneously. And again, those are pretty fast and pretty good. Now, the final option is the custom code. Now, these are the special routines. So basically, I've defined 3. There's one unused version. You can write your own if you want. So what are they? Well, the first one we're going to look at is the double draw. So this is basically using half the amount of pattern data. This was, I use this because in my Suck Hunt game, I did a silly introduction that was a parody of Operation Wolf. Didn't have enough memory left though, so I thought, well, what can I do? And the simple solution as well, if I halve the height of the pattern data, it'll look almost as good and it will save half the memory. And so that's what I did, and it made something that wouldn't fit very easily, so a big bonus there. So I've included that in this, and it's very straightforward. So instead of multiplying the source pattern number by 16, we're multiplying it by 8. It's worth noting though, this time the first byte is actually there are only 2 bits left of this after we've taken out our 2 command bits here. So it's only these top 2 bits here these bits here that are actually part of the pattern number. So they're actually the high byte in the case of custom code, and the second byte is the low byte. So we're multiplying that low byte effectively by 8 because there's 8 bytes per pattern for our double height patterns. And then all we do is we draw the data to the screen in the same way as before. We just pop it off half as much. Very straightforward, really. So that is it's going to be very slightly faster, and it more importantly uses half the memory. Okay, now one that is far more important for speed is our fill option. So the fill is going to just use 2 bytes. Now we read in 2 bytes from our source data, and we write each byte twice on alternate lines. So the first line is entirely filled with the E byte, the second line is entirely filled with the D byte, and then we repeat. And the reason for that is so we can give a nice checkerboard effect, can simulate colors and things like that. So very nice alternative there. The source pattern data is actually just used as is from the source. We don't even multiply by 2. There are sort of 2 bytes drawn to each line, but as alternate pairs can produce nice effects, rather than using 2 and multiplying the pattern number by 2, we actually you just use it as is, and so we could use alternate bytes like that as our fill, which does, as I say, give a nice effect. So still worth doing. So there we go. So that's the fills option there. They're definitely far faster than any kind of pattern data, so definitely worth considering there. The last option is the transparent option. Now let's have a look at that. Now there's sort of 2 options here basically. So we read in the tile number here, and if that tile number is 255, then that is effectively a completely empty tile. Now, to compare to 255, we do inc A, that will roll round to 0 if it was 255, and that will set the 0 flag. That's 1 byte smaller than doing a compare to 255, so a little trick there for saving some memory. So in that case, we are just going to flip the shadow registers and return, and it completely empty tile 255 is defined as. Anything else is transparent though, and a regular tile. So in that case, we're undoing our compare to 255, because as I say, we basically did an inc A there to compare to 255, so we need to reset our tile number here. We then effectively multiply it by 16 here, add our DE source pattern data, and then we've got roughly the same as our previous example, but there's a difference. We are comparing here to the accumulator, which is loaded from the C register. C register is being loaded with 0, and so we're effectively comparing to 0 here. And if the byte that we read in from the pattern data is 0, we are not drawing it to the screen. Now this creates, this is a 0 byte transparency I call it, and it creates a nice cartoony effect for the sprites, I find, because they tend to have a bit of a black border but look quite nice. Now the reason we are using the C register here as our source here, and we're reloading that each time, is because there are maybe cases where you want to use black in your sprite. And so if you were to use self-modifying code and to modify this byte here with a different value, like maybe 255, or what I often did in Chibi-Yakimas was a rainbow byte. That's where color, where the first pixel is color 0, the next pixel is color 1, then color 2, then color 3, or vice versa. And this is a very rare combination that's unlikely to appear in your sprite, and it means you can have a black sprite and still have transparency. So by using C here and loading C and then comparing to it throughout the code, it means that C wasn't free, but it gives us that extra flexibility, which I think you will benefit from. So that's why I've done it that way. But as I say, very simple transparency here. The alternative is to use a lookup table and masking, but I find that with the cartoon data I'm trying to create in my games, this is more than adequate, and it's pretty fast. Not as fast as not drawing the tile, of course, but if you want transparency, this is about the simplest you can get. Anyway, that's all we've got today. Go to the website, down the source code, the build scripts, and use it in anything of your own. As I say, if MaxTile is pretty complicated, and I kind of suspect that if you are at the level where you want to use something like that, you probably don't need my tutorials. You could probably write it yourself, but you know, feel free to download the example code for today and just take parts of it. Just take inspiration from it, whatever you can, and you're welcome to use it in your own code, your own projects. Even if they're commercial, you don't need to give me credit. You're welcome to it. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.